For our fourth video, we're going to take a step away from looking at butadiene and look at rings. And this video is really all going to be about electron donation and electron withdrawal. Okay? Seeing when we have a benzene ring, how does that affect substituents on the ring and the effect on pKa values? Right? So that's where we're going to pick right back up, okay? Thinking about pKa values that we've already learned and now looking at the effect of delocalization, right, which was alluded to in the first video, right? We know we have this big pKa difference between a carboxylic acid and an alcohol, even though the acidic hydrogen is attached directly to oxygen in each case. And if you recall from early on this semester, we said the more stable the conjugate base, the more acidic something is. Or to say it a different way, the more stable the base, the stronger the conjugate acid we have. And we know that a carboxylic acid is a stronger acid than an alcohol because the conjugate base, right, a carboxylate for a carboxylic acid, has delocalized electrons, right, and two stable resonance contributors for a carboxylate. Versus ethoxide here, the conjugate base just has localized electrons. Okay. And I just mentioned this, right? Two stable resonance contributors for carboxylate, which is more stable than just one for a carboxylic acid, okay? Which we've already talked about that in previous videos, right? Delocalization energy makes that carboxylic acid want to be acidic. But now we can think about delocalized electrons even further and compare something like phenol versus cyclohexanol. Okay? And there we see a difference in pKa of 10 versus 16, even though it's an alcohol in each case. And again, phenol is more acidic due to an increase in delocalization energy, okay? Which is really what this is all about. There's a little bit of a higher degree of electron withdrawal, right? Inductive electron withdrawal. Because I have an sp2 hybridized carbon here versus an sp3 hybridized carbon over here. And remember, something with more s character is more electronegative, so it's going to withdraw electrons inductively a little bit stronger, in this case being sp2 hybridized. But really the difference is all about delocalized electrons. Okay? Because when we look at the conjugate base of cyclohexanol, the electrons are localized. But for phenol, right, look at the phenolate ion after we drop the hydrogen. It can delocalize electrons all the way throughout the ring. It has 5 resonance contributors to the phenolate ion, meaning that it's a more stable conjugate base. Right? So phenol is a stronger acid, which is not to confuse it with a carboxylic acid. Okay? 3 of these resonance contributors down here, right, have our charge on something that's not the most electronegative. Okay? And 3 on here on phenol, right, have separation of charge here in the middle. Okay? So it's not as acidic as a carboxylic acid, but the corresponding delocalization energy here, right, and the fact that the phenolate ion has greater delocalization energy than phenol means that this is more acidic than a normal alcohol. Right? So make sure you know how to draw these different resonance contributors come exam time. Let's look at another example. Okay, protonated aniline when it's on a benzene ring versus protonated cyclohexylamine. Okay, so the only difference is cyclohexane versus a benzene ring here in the middle. And again, we see a difference in pKa units, 11.2 versus 4.6. Why is that? Well, with protonated cyclohexylamine, right, when it loses an electron, acts as an acid, loses a proton, forms cyclohexylamine, which has all its electrons localized. However, right, aniline, when it loses, protonated aniline becomes aniline after losing a proton, right? This is aniline, by the way, right? benzene ring with an NH2. Benzene ring with an OH is called phenol. A lot of those one substituents on benzene have special names, so you want to get used to using those. Aniline down here, again, has 5 resonance contributors. More resonance contributors than aniline did, so the conjugate base here has a greater delocalization energy, which is why aniline is acidic. So we can put those two on our table from chapter 2. Everything that's up and around the sides here you already knew from way back in chapter 2, but 2 more to know moving forward if we're predicting how a reaction is going to occur. Know that phenol has a pKa of about 10, and protonated aniline has a pKa of about 5. Right? So just kind of put that in your mental repertoire. But now the question comes, how do substituents affect these things, right? What if I have more substituents going around these rings? How's that going to affect the acidity? And that's what we talk about for the rest of this video, those electronic effects. Substituents are important because substituents can either donate to the ring or withdraw from the ring. Electron donation destabilizes the base, okay, and therefore decreases the conjugate acid strength, which is what's going on the left-hand side. Over here, electron withdrawal stabilizes a base and therefore increases the strength of the conjugate acid. Because again, it's all about the stability of the conjugate base. The more stable the conjugate base, the stronger the acid. And we're thinking about electron density. So something that can pull that electron density towards it, substituents here, right? Z is the substituent. We're looking at phenolate ions here. If it pulls that electron density away and helps, it makes the conjugate acid stronger because it's stabilizing this thing. It does the opposite, right? That's like adding heat to a fire already. It's destabilizing this thing. So how can I stabilize something? Well, it can happen by inductive electron withdrawal. That's old news from chapter 2. I can have a substituent that's more electronegative than hydrogen, and it just withdraws electrons inductively through the sigma bonds. So that's one way to withdraw electrons. If it's the thing that's directly attached is more electronegative. But resonance is really where we need to look for what's going on, because electrons can either be donated by resonance or withdrawn by resonance. And these are the money makers looking at substituents. Here, right, if a substituent, and another example is if you see a substituent that has a lone pair on the atom that's directly attached to the ring, okay, so not further up the chain here, whatever's directly attached to the benzene ring, if that thing has a lone pair, then it's possible for the lone pair to be delocalized into the ring, as we see here. All right. So that is donation by resonance. Okay. But as we're going to see here in just a second, right, there's also a balance because oxygen is more electronegative than hydrogen. So oxygen's withdrawing inductively, but donating by resonance. Let's look at another example here on 73. This is withdrawal by resonance. And you see this when your substituent that's attached to the benzene ring here doesn't have a lone pair, but rather has a double bond or a triple bond going to something else that's more electronegative. Okay, so here we see a double bond to oxygen. If you have a carbonyl group, a cyano group, a nitro group, things like this, these are the common substituents you see that withdraw electrons by resonance. See here, it's pulling electron density out of the ring in these resonance contributors. Okay? And nitrogen's more electronegative, so it's withdrawing inductively. So look for that, right? Know these 4 substituents because they withdraw by resonance and they withdraw inductively. Okay? So those are the easy ones to identify. That's what's shown down at the bottom here. Those are the strongest acids. Okay? Other things here, we're comparing relative to an unsubstituted phenol. Halogens, for example, we know they withdraw inductively because they're more electronegative. However, right, they also have lone pairs, so it's possible that they could donate to the ring. So that's something that has to be determined experimentally, just like a methoxy group. Okay, it's more electronegative, so it can withdraw inductively, but it can also donate into the ring by resonance. And it comes down to the degree to which they do both. Okay, compared to an unsubstituted phenol, if I put on a halogen, I get a stronger acid. If I put on methoxy, I get a weaker acid. So that tells me that for a methoxy group, the donation by resonance outweighs the electron withdrawal versus a halogen, right? The inductive electron withdrawal outweighs the donation by resonance. So you should draw a line here in the middle. These here are weaker acids. These bottom two are stronger acids. Okay? And then a methyl group, right, donates electrons by hyperconjugation. So that gives you a weaker acid. So if I put them all together, okay, a methyl group and a methoxy, notice my acid has gotten weaker. A halogen, a carbonyl group, or an NO2, that makes them stronger. So those are the groups that are shown on slide 75 and 76. And I'll expect you to know that. Okay? Know the approximate pKa of an unsubstituted protonated aniline and an unsubstituted phenol, but also know, not the exact values, but if you put on a halogen, a carbonyl, or a nitro group, or a cyanyl group that's also listed in the slides, that makes it more acidic. If you put on a methyl group, or a methoxy group, or an ethyl or an ethoxy, anything like that, that makes it a weaker acid. So those are the big takeaways from this video, right? Know those effects on acidity, because we're going to use that to predict reactions moving forward in Chapter 8.